I'd like to start generalizing this process that we did with looking at approximating areas using rectangles to be able to say what is it true for in general for any function using either the left or the right endpoints using any type of width that we would like. Okay, so we looked at concrete examples. Let's take a look at it in general. So if we want to generalize the process of finding the approximate area under a curve given by f of x, now as a note, we're going to assume that f of x, this is going to be a continuous function and is non-negative. So we're not going to go underneath the x-axis yet, and we're also not going to be dealing with any type of discontinuities. We just have a nice, smooth, normal function. So, and we're going to be kind of having the cutoffs at x equals a, x equals b, using n rectangles of equal width. Okay, so if we want to generalize this process here, notice in all of these we have a sum, right? So we have some type of sum, and with that sum, the sum indicates the area of each of these individual rectangles. So if we were to look at an arbitrary function, say like this, and I'm cutting this off at A, cutting this off at B, I would like to be able to create rectangles based off of this. So let's say we have n rectangles, so I don't know whatever that would be. So I'm going to form the widths like this. In this case, n would be 4. Remember, when we looked at these, we were able to calculate the width of each of these rectangles, right? So there's 4 of these widths of the rectangles. So that's one thing that's easy to calculate, is that if this total distance here is b minus a, and we're dividing it into n rectangles, well, we could find the width of each of these rectangles. So we have the width of each rectangle would be calculated as b minus a divided by n. So the width of each rectangle is going to be b minus a divided by n. Now for notation purposes, I'm going to call this delta x. This is going to be the change in the x values because we're just looking at widths in the x values. Now the height is going to be determined by the function value at any of these points. So we talked about right endpoints. We could define the height of the rectangle based off of that. We could define the height on the left ones, the left endpoints, and it would look like that. We could also define the midpoint if we wanted to. We could find the middle and then find the area based off of that point. But nonetheless, the important part is that all of the heights are determined by the function at some point. So that's what we're going to use. So the width of each of these rectangles is this, and then the height, I'm going to call this f of c sub I. So the function at some value. So I'm using the c sub I to indicate that I'm going to have these, I is going to go from 1 to 4. So it's going to be, there's going to be 4 of these that define the height. So with this, I can now piece all this together to give me my area formula. This is, again, this is the approximate area. This is going to be the sum from I equals 1 to n. So again, if we have n rectangles, I'm going to be adding n of these smaller, I'm going to add n of these areas together. So for each of these, I take the width times the height. So I take f of c sub I times delta x. And so this is in general what the formula is going to look like for any function when we define our width to be this, equal width, and we're choosing our c sub i's in some type of manner. So how we want to choose these, if we again look mostly at the right endpoints and left endpoints, what I have over here is I'm going to define the c sub I based off of what I know about a and b and n and all of that. So the right endpoints, the first one, remember these all depend on I, the first one is going to be this one in this case. So it's based off of A, but I'm going to have to add on a copy of the width, right? If I want to use the right endpoint for this second rectangle, I'm going to start at A, and I'm going to add on 2 copies of the width. Next, I'm going to have on 3 copies of the width, and so on and so forth. So for any I, for any of these, I'm going to start with A, and then I'm going to add on a certain number of copies of delta x. So I'm going to add on a certain number of copies of delta x. Now what that would be is, for my first one, I add on 1 copy of delta x. My second right endpoint, I'm going to add on 2 copies. So this is going to be I times delta x. So this c sub I is what we can plug in. Now we could also refer to this as the same as a plus I times b minus a divided by n. So either way, we can use these. So it depends on what we're given and what we're trying to find. These are just interchangeable with each other. So the left endpoint, we said that's a little bit different. We looked at those examples where the i's get a little funny when we write it in this summation notation. But in this case, my first one needs to start here at A. My second left endpoint will start over here when I add on 1 copy of x. My third left endpoint, I'm adding on 2 copies of x. So I'm always adding 1 less copy of x than which of these, I guess, number of these I'm using. So the only difference is I'm going to start with A, but I'm going to add on I minus 1 times delta x. Or this could be seen as A plus I minus 1 times B minus A divided by n. So we have these, so you could now just use this as a very straightforward example of applying this to our left and right endpoints. So if we look at an example, if we looked at, say, f of x is equal to negative x squared plus 5, and we have between x equals 0 and x equals 2. So we saw these examples before. Using these formulas now, if I want to use the right endpoint area, so the right endpoint area, this is going to be the sum. Oh, and I guess if we're going to use, say, n equals, we'll do 5. We'll do 5 rectangles. I is going to go from 1 to n, which in this case is going to be 5. So I go from 1 to n. I have my f of c sub I. My c sub i's are defined by this. So if I know b, this right here would be my b, this right here would be my a. I know n is going to be 5. I have a is going to be 0 plus b minus a, 2 minus 0, divided by 5 times I. And then I multiply this by the width, delta x, which we said is b minus a over n. So I take 2 minus 0 over 5. In simplifying this, I have the sum from I equals 1 to 5 of f of 2/5 I times 2/5. And so we saw this formula. This is what the formula looks like in general. And now you could simplify this, plug in this into the function if you'd like, and take sums, combine everything, and get your areas. Now, this is always based off of approximate areas. Remember, we're just estimating the areas. We are not finding the exact area at this point. Remember, we've seen that there's a lot of error between how these rectangles aren't perfect, right? This is not a rectangular region, but we're trying to use a rectangle to approximate this. So we would like to figure out, how do I go from approximates to exact areas? How can I use anything we've done in calculus to be able to go from the approximate to the exact?